Hi all, this is Mr. Yeager for AP Physics, and this is the last video I have for the fluid unit. We're going to look at fluid dynamics, Bernoulli's principle, continuity law, whatever you want to call it, and we'll go from there. Okay, so with fluid dynamics, okay, we're moving now to the water. The liquid is actually flowing, it's actually moving. So one of the biggest things for fluid dynamics is this idea that mass must be conserved. All right, it seems kind of like, oh my gosh, where does this come from all of a sudden? Because that's a huge chemistry concept, obviously, in terms of balancing reactions. Stoichiometry and everything is that we should have conservation of mass, but should hold true in this situation as well. We can't have all of a sudden more fluid at one point in the system versus at another point all of a sudden there's less mass. So we need to account for all of this. Some of the other things that we deal with is we do not do compressible fluids. Water is not compressible, okay? We call this an ideal fluid, all right? There may be some situations in the real world where fluids can actually compress ever so slightly, but we have to remember from the standpoint of liquids as a state of matter, they're already very tight together. Okay, it's not a gas where there's mostly empty space and that you can compress that. Just like a solid, there's no more space for them to compress. Okay. Another thing is volume will be conserved. Again, if I'm conserving mass, I'm conserving volume, which means I'm conserving density. I mean, I don't even want to say we conserve density, but the idea is obviously the density of the liquid from one point to another can't change. Okay, because it's the same liquid the whole time. So one of the first formulas we get is what's called the fluid flow rate, okay? And this is, we have the symbol Q for. Again, why it's Q, I don't know, all right? But the fluid flow rate, basically we're saying how much liquid is passing over time. So volume divided by time, this is gonna be measured in meters cubed per second, okay? This is gonna be important to illustrate the conservation of mass, which we're gonna see on this next page, okay? So, what we introduce is what we call the continuity equation, okay? This is basically explaining that the mass that you put in to an area has to be the same mass that comes out of that particular area, okay? So we have to have conservation of mass throughout the flow of a liquid, okay? You cannot just have some of the liquid just disappear in terms of it, all right? And so this will affect how much fluid goes by. And that's why we're saying that Q1, the flow rate in one area, has to equal the flow rate in another area. And so what we have there is we can expand that formula to A1 V1 equals A2 V2, okay? So where do I get that from, okay? So we start off with our fluid flow rate formula, V, volume over time, okay? And I'm going to change volume to area times distance. Again, we saw this with area times height back with pressure, okay, when we were calculating now pressure parts. So I'm going to just, again, volume is length times width times height, so I'm just pulling out one of those distances and then still combining the other two for the area. So you can see now I have area 1, D1, over T equals A2 D2 over T. Well, what does basically distance over time equal? Okay, if I combine distance over time, that's velocity. Okay, it's flowing at that particular constant velocity, that instantaneous velocity at that time. Okay, and so we now have A1 V1 equals A2 V2. That is our continuity equation. Very important equation. Okay, in terms of what we're going to use. And I'll show a couple little simulations just to try to illustrate that some. Okay, so what this is saying is if I decrease the area that the liquid has to try to flow through, that means more of it has to flow, it has to flow faster so that I have the same mass amount going through that particular area as I do in the first part. So again, it kind of makes sense in terms of we usually have these wider pipes usually at the bottom of buildings, and the pipes get thinner and thinner as they go up, and that helps get the speed to go faster as it goes up. Okay, that's how we try to maintain that pressure, essentially. Okay, obviously if there's not as much fluid flowing through, that's not because it's having a hard, obviously, you have that push going up, but that means there's not as much flow at the bottom either. It's not just at the top of the building, the top of the house, the second floor of the house, but it's everywhere, okay? So one thing to be ready for with AP questions in this is they like you to solve how velocity relates to area and how that relates to radius. So they're going to say the radius of the pipe is going to change this much. How much will the velocity change by? Okay, so I have an example here, okay? What we need to remember, as we get to this example, is that these pipes, they are circular areas. Okay, I understand they're cylindrical volumes, but they're circular cross-sectional areas. So radius is our squared relationship that we get here. So our example, a fluid flows through a horizontal pipe with varying diameters. At point A, that diameter is 4 centimeters. At point B, it is 2 centimeters. If the pressure at point A is 150 kPa and the velocity is 2 meters per second, calculate the velocity at point B, assuming incompressible flow. Incompressible flow, basically meaning it's not changing, obviously pushing the fluid together more. All right, so they give us diameters, but we know diameter or radius is just half of the diameter. So I mean, yeah, if I half the diameter, I half the radius. So what do I have here? I'm introducing my continuity equation, A1V1 equals A2V2. I know the area is pi r squared. So I'm decreasing the radius by 1/2. So in my formula for the area, that means I'm decreasing the area, excuse me, you get to hear me sneeze, is 1/4 change, okay? There's a 1/4 change. So I have the other side. I'm not messing with the left-hand side of this equation, but I'm changing that the area that this object has is 1/4 the amount. All right, the factor is changing by 1/4 because of the squared radius. All right, so if that changes by 1/4, that means my velocity must increase 4 times. All right, so that both sides of the equation, if this, again, be very clear, if this changes by 1/4 and I'm not changing the other side, I'll just make that 1, I need to change velocity by a factor of 4 so that the flow rate remains the same, so that the same amount of mass travels through every part of the pipe, okay? And so I can just simply multiply that. 4 times 2 is 8 meters per second. All right. The pressure is really nothing that we're dealing with at this time. Okay. Well, at this time, we don't need to worry about the pressure. That's just something. I mean, that's just extra information to make you think, oh, do I need to do something with that? No, that's not. Pressure is not in that formula. We will see in a moment, though, on the next page, that pressure will actually change as well. Okay, in terms of this. Okay. So that is the continuity principle. So let me show you a couple things here. Not that. Let's try to find where I want to go. Okay. Again, I like going to some of these PhET simulations. Okay. I'm actually going to use this one from Physics Aviary first. This is basically what we're trying to show here. Okay. I like how this is going with it. Okay. And I'm going to really decrease the radius a lot so we can kind of see the change here. Okay. All right, so you can see what's going on here. This is showing you, hey, on the left-hand side, I have a larger radius, okay? And therefore, it's not going to, and then I decrease the radius. If I decrease the radius, I have to increase the velocity, okay? I have to increase the velocity as it goes through as well, okay? So, I mean, this is just a kind of a good, simple one to start with. Again, you see more, like it's not more particles, they're just traveling faster so that the amount of particles on this side, the amount of mass, is the same amount of mass on the other side as well, okay? There's a PhET simulation as well that does this very nicely, okay? Where you can see with this, and maybe it's a little bit bigger, but this is where, I can mess with the size of the pipe at different points. And if I make this part of the pipe really small, or maybe I make all this a lot smaller, I'll just make it all smaller. Obviously, it starts flowing faster, okay? It has I was about to say the flow rate, okay? But the flow rates actually on both sides are the same because the volume over time is the same, the velocity of the particles over on this side where it's thinner is faster, is larger. Okay? All right. That leads us to, finally, our last big principle here, okay, is Bernoulli's principle, okay? And Bernoulli's principle states where the velocity of a fluid is high, the pressure is low, and where the velocity is low, the pressure is high. That right off the bat, I think to a lot of people doesn't make a lot of sense. How can the velocity be fast, high, with the pressure low, okay? And that's why I immediately ask. That seems very, very odd, okay? The thing is, we have to think back to the idea that fluids are going to travel from high pressure to low pressure. Okay, it's this pressure that is making it move from one area to another area. It's just like you talk about in biology with osmosis or diffusion, that water is going to flow from an area of, we say, low concentration of salt to high concentration of salt. I know that's confusing, but the idea is it wants to move across that membrane, the osmotic pressure that's created. All right? And so the greater the difference between the two, the higher the osmotic pressure and the faster the flow is going to be from the high to the low side, okay, where the pressure is occurring, all right? There's a high pressure occurring on the side where there's low salt, and there's a low pressure on the side with high salt, and that's the direction of the flow, okay? And so pressure is what's providing the force, which this is where I'm trying to help you out with it to understand, okay, again, I'm confused. Why, if the pressure's high, the velocity is low, okay? The idea is those particles are going to be pushed faster and faster and faster toward the lower pressure. They are being accelerated toward the lower pressure, so when there's low pressure, those particles are going to go very fast. If there's low pressure, the particles don't want to go backwards into the high pressure. There's no force for them. There's no net force for them to move that particular direction. So they are being accelerated the entire time from high pressure, where they're moving slowly, to a low pressure, where they're moving fast. Okay? Yep, there we go. Therefore, the velocity should increase. All right? So I'll go back to my videos again with this, or my simulations. I'll use this one because it's kind of the easier one to read. All right? If we look at this, on the side where it's slow, it's saying it's something like, what's that, 320? It's at 320 kPa at the low, there we go, at the area where there's low velocity. At high velocity, you can already tell that's gone down. The pressure is now 250. So there is less pressure where there's a higher velocity. All that pressure has been used to accelerate the objects, the fluid, to the other side. Okay? Excuse me. And we can see that with this too. If I bring my pressure gauge down, and I know this is also dealing with the height, so I'm going to try to stay at one line here. But 115, 115, 115, 115, 115, it's all pretty similar because now it's getting a little thinner, it's getting thinner, it's getting thinner. Area where it's really thin, the pressure drops dramatically. So that's Bernoulli's principle. So high pressure where the velocity is low, low pressure where the velocity is high. So this ends up relating also to energy. And you can see we are left with our Bernoulli's equation, which is a conservation of energy equation. Okay? We have P1, pressure, at 0.1. So again, I love these conservation of energy equations because you can sit there and be like, this is the initial settings, and this is the final settings. And you can figure out, and you can kind of focus and not worry about what's happening in between by going, hey, over on this side, what is the pressure that this object is feeling? What is the atmospheric pressure? That's sort of what you're looking at. Okay, what's the absolute pressure? All right, actually, it's just actually this would just be atmospheric pressure. Sorry, because the absolute pressure is the combination of those two. All right, but yeah, what's the atmospheric pressure outside? Okay, toward what's the atmospheric pressure when the water is released from a particular area. We're going to do a problem where this is like the water tank example. Okay, you're going to hopefully do a fun lab where like the water spits out. This is like a water fountain lab too, and things like that. So that we have the atmospheric pressure plus the pressure of the liquid You can see basically that's the energy of the liquid in some ways too, okay? Rho gy plus 1/2 rho v squared, okay? Which clearly is the velocity. It's basically, again, this is not necessarily kinetic, but it's very much related to the kinetic energy of the liquid at that point. How fast is it flowing at that point or coming out at that point, okay? So that's what we basically have. Again, it looks very similar to our mgh plus 1/2 mv squared formula. So it combines everything that we're basically going through. If there's an increased speed with a decreased pressure, all right? Basically, if I'm looking from one side to the other, and maybe I'm not changing the depth of the fluid, okay, or the particle in the fluid. If I decrease the pressure, I got to increase the velocity, okay, to keep this conserved all the way across the board. Increased depth equals increased pressure. All right, why is pressure in the equation? It's basically representing the work that's involved in the problem, okay? And so I'm not, again, I want to say it is creating some sort of work, okay? It's taking the place of work. And work done by pressure can be rearranged into this formula where instead of force times distance, I'm doing pressure times area times distance, okay? Is what we're looking at there. So we have a question here. Water flows from an open tank or a large tank open to the atmosphere through a small opening at the bottom. If the water level is 5 meters above the opening, calculate the speed of the water as it exits the tank. Okay? So if I made just a quick little drawing of this, the idea would be something like this. Is there some valve at the bottom and the water is 5 meters up at this point. Okay? Now, this is the instantaneous speed at this particular point. I understand. Think about what would happen if this starts going down, down, down. I'll show this in one of the sims in just a moment too. What's going to happen to the speed of the water? It should decrease, okay, as it keeps going down because there's not as much in it, okay? So if I go through this particular problem, again, pressure doesn't change, okay? The atmospheric pressure at the beginning and at the end doesn't change. I only have the water is not moving, so at the beginning, so there's no velocity, V1, but there it does have this basically potential energy, and then on the other side, I have just the water at the very bottom. So pretty straightforward problem. The velocity should equal 10 meters per second when it initially comes out of the out of the tank, when it initially comes out of the tank, okay? I want to do another problem just to kind of go through some things, and then I'll show a couple last sims with it. But let's say I have this problem, another water tank. You can see the water tank is filled to a height of 15 meters. The valve's at the very bottom. Okay. The first question is just find the absolute pressure that this is feeling. Find the absolute pressure with the valve closed. Basically, I should have said that, with the valve closed. So for this one, what I would do simply is for part A, I'm solving for absolute pressure, which is equal to the atmospheric pressure plus rho g y. Okay, rho g y or rho g h. And so atmospheric pressure, again, we use the 100,000 newtons over meter squared. That is our atmospheric pressure, 1 bar, 10 to the 5th, plus water, 1,000 times 10 times 15. So the total absolute pressure acting on it at this time would be 250,000 Newton over meter squared. Okay. All right. Part B. What is the speed of the water when the valve opens? So here I'm going to Bernoulli's equation, okay, where I'm going to write it all out. Oops, kind of threw that one the other way. That's okay. Equals P, right, P1, P2, plus rho G Y F Y naught, or Y1, whatever. I'm switching my, come on, Mike. There we go. 1/2 mv squared. There we go. All right. So with the valve opens, that means the atmospheric pressure that this is feeling here is the same at the bottom. So pressure cancels out there. Okay. The atmospheric pressure is now equal at both points. what do I have? I have this initial depth of the liquid at this time. It's very similar to what we just did. I can cancel out that there's no initial velocity of this liquid. It's coming out on the ground, so guess what? I'm basically showing you the exact same thing again, just with a different problem. Okay, and densities cancel out, and I'm left with 10 times 15 equals 1/2 VF squared, and this comes out to VF equals 17 meters per second. Okay, is what we're looking at there. All right, or basically about 17 meters per second. All right, last question. What is the flow rate? What is the flow rate? So flow rate, I understand, is equal to volume over time, but it's also equal to area times velocity. Area times velocity. I just found my velocity at the bottom is 17 meters per second, so all I'm doing is calculating the area. An area of this circular, I know I made it kind of a square, I'm sorry, but it's circular, okay, is pi r squared. And the only thing we got to make sure is this is centimeters, so it's pi times 0.1 squared, so that's going to equal 0.031, and I multiply those together, and the flow rate is 0.53 meters per second. Meters cubed per second, sorry. Okay, it's still volume. All right, meters cubed per second is how much is flowing by. So that's just another sort of version of this problem. Some other things that you might run into, is that I'm just going to kind of just qualitatively look at with this particular sim. Sorry, let me try to get it organized here. Let me just reset it. Reset is you might have a situation where they do give you the different, pressures and everything of what's going to happen as it gets lower and all that stuff. So like if I try to raise this on up, trying to make this where that's up high, okay, and then it gets thinner as it goes down, okay. They'd have to give you some information here, or they'd be like, hey, the pressure at this point, at point A is 115, the pressure at point B is at 114.5, okay? So you do have a change in pressure. They give you the velocity over here, they give you the height. We'd have to give you all that information, and you could go down and end up figuring out the velocity that the particles have as they enter the tube on the other side. Again, they try to keep this where it's like a consistent cross-sectional point on the same plane, so like there'll be like point A right here and then point B over here, all right, and discuss the different changes that occur. But that's something, again, you can just use Bernoulli's equation to solve for. The last thing to be very much ready for, okay, is a problem, is a problem where they're going to connect this fluid flow rate and Bernoulli's to basically the idea of to projectile motion, okay? If I could try to, okay, feel that. All right, there we go. All right, and this is definitely something that they'd like to make you try to figure out and be like, where will the water hit the ground? So we're going to use Bernoulli's over on this side. Okay, I'm just going to write Ber. We're going to use Bernoulli's over here, and then we do basically 0-degree projectile launch on the other side. I am not writing very well. 0-degree projectiles on the other side. And so we can use the combination of those two things to kind of expand the problem a little bit and make you figure out the range, okay, the time in air, et cetera, okay? Now, this is what I wanted to briefly show too. If you can see I'm constantly matching how much is coming out, so that's why it's staying at one distance, okay? If I don't and I let the water start just going down, obviously you'll see that it's not going to travel as far anymore, okay? And again, we could go ahead and figure out and be like about what level does the water have to be to make it go half the range and things like that. So that's something you can kind of obviously look at, okay? So again, you can see that the energy is decreasing because there's not as much water. The flow rate's decreasing. Okay. So that's what you're looking at with it. All right. So that's all I got. Hope you enjoy. Again, this is from FET, and the other one is from Physics Aviary. Both excellent sites to play around with, and that's about it. Thank you.